On behalf of Jan Arenhammer, I'm Chris Ford, and this is System Fail, a review of the systems approach as a decision-making method for lifeline infrastructure systems. This paper reviews the systems approach as the prevailing decision-making method responsible for shaping the majority of infrastructure used in the United States today. This paper identifies a bias for the system as a solution type for urban infrastructure, explains the systems approach as a thought model and process for decision-making, and advances people-centered mindsets will be essential for designing next-generation infrastructure solutions appropriate for 21st century urban futures. The city remains the strongest material evidence of our human desire to dwell collectively, yet the development of each city as a place-specific environment for urban dwelling necessitates the co-development of its respective infrastructure systems. Similar to an ocean liner, cities also require life support systems to enable sustained human habitation. While the boundaries of lifeline systems are evident within a contained vessel, the extensive urban systems are either beneath or beyond visible range, as they often exceed municipal boundaries. The implementation of urban infrastructure is the responsibility of a range of stakeholders and decision makers. First-generation modern infrastructure systems were brought online around the year 1890 and were built according to then good engineering practice with a service life expectancy of 50 to 75 years. At their moment of implementation, however, there was no corresponding plan for system repair or replacement. Fortunately, some infrastructure was deliberately over-engineered with generous safety factors, and this in part explains how some infrastructure performs beyond its planned service life. In this Anthropocenic epoch, characterized by strengthening hazards, however, an imperative for persistent operation prompts greater consideration of resilient, decentralized solutions for delivering critical resource units to urban dwellers. Must decisions regarding next-generation urban solutions be resolved by members of other disciplines, or is it reasonable for urban planners and architects to practice disciplinary promiscuity and lead the development of superior urban solutions using the best of their own disciplinary skill sets? It seems pertinent to first understand the historic primacy placed on the system as a form for infrastructural implementation. In the interest of questioning the system as a design strategy and investigating its associative tactics for infrastructure implementation, the following questions are posed. Effective definitions of a system share certain elements. The first three were published between 1973 and 1975 within larger discussions about the systems approach. The last one, by Donella Meadows in her title Thinking in Systems, includes similar elements, but with more qualification and nuance for improved application to a greater number of system types. Meadows' definition lends itself well for recognizing systems that are either physical, such as the human body, or non-physical, such as a legislative system. Each of these definitions acknowledges the compositional relationship between parts to whole. Whereas each component of a system can be read as a singular entity, its properties and features also signal a role in the making of a larger entity. Depending upon the scale at which a system is examined, it is likely multiple systems will be found working simultaneously, and sometimes with interdependent relationships. This is certainly true for both the human body and the urban corpus. The basic behavior of a system is demonstrated through the bidirectional translation of a type of flow into a system stock, or vice versa. A stock is a store, a quantity, an accumulation of material or information that is built up over time. For lifeline infrastructure systems, critical resource units, such as kilowatt hours of electricity, are system stocks for the duration these units reside within their respective system. A flow is stock within a system measured as either inflows into the beginning of a system or as outflows at system end. All implemented systems negotiate with and operate in specific environments. The water systems serving Saudi Arabia, Michigan, and California feature some similarities while also expressing peculiarities. Importantly, a system bounds itself from the larger environment within which the system is positioned. These environments then often present context-specific hazards, inducing an informative feedback loop for resilient design requirements prior to system implementation. Systems can also introduce impacts to their environments, and infrastructure planning has historically been challenged to anticipate their full range once operational. For instance, the environmental and social costs associated with elevated freeways in Boston and San Francisco are well documented, as well as the rediscovery of benefits when these same freeways were demolished. Also, a stronger appreciation for environments as realms of use may raise emphasis on the usability of system outflows rather than on system expression and self-embodiment. As a method for engaging urban design problems that were increasingly complex and dynamic, the systems approach emerged as a preferred tactic. Origins of the systems approach have been traced to operations research during World War II and its application to the built environment through the functionalist movement. The systems approach is a procedure-based thought model for problem solving. Dickerson and Robert Shaw have characterized the systems approach as a plan for making plans, while Ferguson described it as a guide for attacking a problem. Whereas the systems approach semantically suggests a methodology for designing systems, it is instead a method for systemic thinking through deliberate action items moving from the general to the specific. In broad terms, it can be understood in 4 basic steps: problem formulation, modeling, analysis and optimization, and implementation. As a method for decision-making, it can be applied to different types of problems, whether a product or a service, yet presents comparative advantage when engaging larger, complicated problems. The systems approach has been embraced as a conceptual framework for facing complexity, as it reflects a search for the interrelatedness of things in any problematic situation. As a planning tool, it means approaching the city as a very complex whole, within which many elements act interdependently. Across the review of multiple authors, however, there are 2 pervasive features that are central to all helpful descriptions: holism in the identification of a problem, and rationality in engaging the problem. Users of the systems approach aspire to consider problems holistically and in their fullness. The problem is identified and developed by taking a general, broad look at the situation, that is, by considering the total system, including its environment. A holistic perspective is extremely difficult to achieve in practice, whether executed as an individual or by an experienced team of interdisciplinary design professionals. Subconscious behaviors, habits, and mindsets work at different moments, strengths, and scales to oppose stated goals and aspirations for altruistic decision-making. Whether knowingly or unknowingly, concentrated attention to a portion of a problem comes at the expense of a more holistic problem definition. This dynamic is characteristic of most 20th century urban solutions, and is especially true in infrastructure design. Infrastructural history contains examples that have introduced detrimental and undesirable effects, creating new social, political, and economic problems to be managed by others at some future moment. Examples in the United States include the removal of streetcars from the East Bay Bridge, Robert Moses's bridge designs on the periphery of New York City, and electrical equipment failures responsible for igniting multiple wildfires across California. The systems approach also requires rationality in both thought and action. When reviewing project materials produced with the systems approach, the expression of this rationality is the most identifiable characteristic of its presence. A key feature of the systems approach is the analysis of inflows and outflows that differentiates this process from others. Increased rationality also prompts a consistent evaluation of possible solutions through the benefits and penalties for each. From a rational perspective, the measure of a benefit is called effectiveness, and the measure of penalty is called cost. Rational decision-making, however, poses challenges of its own. Anticipating consequences is valuable for the design of urban systems. However, a paradox of rationality emerges. The anticipation of consequences of decisions is consequential by itself because it requires additional time, labor, and money to trace. When taken to an extreme, there are certainly penalties for hyper-rationalization. Heightened emphasis on economy and the preservation of resources during the design process can also be detrimental to long-term operations of infrastructural asset classes. In particular, planning processes are considered efficient when labor, materials, and services as input to the process are reduced to minimums. As administrators of infrastructure are already challenged to accommodate increasing demand with less financial resources available, recent infrastructural failures prompt a reconsideration of fiscal priorities required for persistent infrastructural maintenance. The recent collapses of 3 bridges tragically foreground human costs when both the design of infrastructural assets is economized and responsibilities for asset maintenance are deferred. A literature review of the systems approach suggests its effectiveness for decision-making is proportional to the degree to which a design problem can be clearly defined. However, multiple design methodologists, including Horst Riddle and Peter Rowe, observe all design problems to be either ill-defined or wicked. The system-centric mindset often confuses solution spaces with the problem spaces from which they originate, and any implied correlation between more tightly defined problems and more ideal solutions implies a dynamic that expert designers will find false and inconsistent with their breadth of experience. To its credit, the systems approach is well-intentioned for making decisions in a way that emphasizes objective and holistic thought. However, a lack of foresight into those future contexts in which infrastructure systems will operate signals a key vulnerability to the fidelity of this decision-making method. There is no fault in being unable to predict the future. For the systems analyst, however, the direction in which one analyzes is, ironically, behind them. Orienting oneself to the past allows for reflection and analysis. Design, however, is projective and therefore not the result of analysis alone. The better one succeeds in being rational, the less one can derive what one should do now. For a thought model characterized as both holistic and rational to bring value to the shaping of the urban environment, then it must incorporate the purview of future contexts for use. There remains an obligation to conclude with notes regarding the systems approach for the design of future lifeline infrastructure solutions. Through systems approach literature, there is an interesting emphasis on a system as a telegraph solution type. Ferguson observes, in practice, we cannot expect different actors to assert compatible definitions of what is to be done with the urban system, nor even to agree on what its problems might be. Might there, however, be some spectrum of creative possibility, made visible as soon as one ceases any expectation for future infrastructure solutions to manifest as either a system or as an extension of one? Urban dwellers have so far tolerated the system-centric mindset in the municipal arena as they continue to benefit from persistent urban infrastructure operation during normal conditions. However, when the environments enveloping these urban systems assert acute and chronic loads, we now witness an increased number of urban system failure incidents, and a change in the paradigm historically used for infrastructural decision-making is necessary. A people-centric paradigm has been utilized in other fields, such as industrial design and interaction design, and may introduce similar gains when applied to the design of future urban systems. In this application, people-centered decision-making requires a strategic, methodological convergence to the demonstrated needs of urban dwellers and developing an ability to anticipate the active context responsible for people's physical, intellectual, and emotional needs. People-centrism explicitly elevates the demonstrated needs of urban dwellers as paramount to other constraints, requirements, and considerations found in the problem space, thereby overcoming some of the key limitations of the systems approach identified by Horst Rittel. If applied to problems of urban systems, then the people-centric process of design thinking would empower decision-making beyond the mere observation of system functions, and include observations of how, when, and why urban dwellers use urban environments. Design thinking also prompts a massive opportunity to prototype design options and test their use in urban contexts. Feedback generated by such design action would be of value exceeding computation-based simulations and public polling. Until superior lifeline design solutions authored by people-centric mindsets can be tested against the infrastructural status quo, urban dwellers remain dependent upon resource unit flows formed by system-centric mindsets for sustaining both an urban lifestyle and human life itself. The systems approach, as a decision-making model, has so far been instrumental in shaping these urban systems. Thank you.